Welcome to the Response-Based Campaign Testing Necessary Statistical Terms lesson. The goal is to review the terms we need to efficiently discuss what we're going to do. What we're going to do is solve the following problem. We're going to try to measure different marketing campaigns, such as sending out sales offer at different price points to different populations. What we want to do is measure the response rate of each population. We have to keep in mind uncertainty and the fact that the rates seen in our samples may not be truly representative of the rates of the underlying populations. We also want to make a good choice of which price point to continue with or which campaign to select. And this requires good design of our campaigns, which is an appropriate selection of sizes for each of the experiments. In our lectures, we're going to use a few technical statistical terms, in particular experiments, random variables, probability, distributions, a notion called exchangeability, a notion called sufficient statistics, summary statistics, and frequentist and Bayesian inference methods. The purpose of the review is to make sure these terms are not surprises when we use them. You may already be comfortable with some of them. If so, this review will just put them in context. If you don't know these terms, hopefully we'll introduce enough that you either understand them or can pick them up as we go or from a reference. An experiment is typically where a researcher controls an environment, sets something out, and measures the response. In our case, we're going to pick one or more price points, each price point called a campaign, and we're going to send out marketing materials. What we read back will be who goes for our sale, these will be called successes, and what rate this happens at, the fraction of successes over total trials or actions. A random variable is what a statistician thinks of as a measurement. In our case, it'll be counts and successes. Probability is defined as the quantitative notion of the chance an event will occur. It turns out there's a lot of philosophy in probability. The more common frequentist interpretation is that the only proper use of the word probability is the limiting rate or frequency of an event happening under a large number of repetitions. The Bayesian interpretation also allows for probabilities called subjective probabilities, which express degrees of belief or prior predictions. And finally, there are also concepts called notional probabilities, which are numbers that are merely used for calculation, which don't represent any observed frequency or even anyone's belief. Notationally, probability is usually written P of x, or Px takes a value. We also will encounter conditional probabilities, which are written as Px bar e, which is called the conditional probability of x given the evidence e, and it is defined as the ratio of both x and e occurring together divided by the probability of e, or the count of number of events where both x and e are true over the number of events where e is true. A distribution is a formula or table relating for each possible outcome of an experiment the probability of seeing that outcome. We're going to work with a number of theoretical distributions. The normal distribution, the log normal distribution, the binomial distribution, the beta distribution, and the Poisson distribution. They have shapes as shown here. A distribution is called discrete if it assigns probabilities only to a discrete set of values, such as the integers instead of every possible real number. Two discrete distributions are the binomial distribution, which is the exact distribution of the number of successes for a given number of trials and a given success rate, so very relevant to our problem, and the Poisson distribution, which is another counting distribution very relevant to our problem. Here we illustrate a related binomial and Poisson distribution, and you can see they're fairly similar. Continuous distributions are distributions that assign non-zero densities to continuous intervals of numbers. Examples include the normal distribution, which is used to drive a lot of tests like the t-test, and also its near relatives, the student t-distribution, is used to drive things like power and significance calculators. The log normal distribution, which is very useful in modeling things like money, and is a so-called heavy tail distribution, which is a counterexample to a number of things that people commonly believe about distributions, and the beta distribution, which turns out to be the distribution of the unknown rates we're trying to measure when conditioned on having seen some evidence or having run an experiment. An important statistical concept is exchangeability. An example is if we sent out K envelopes in our marketing campaign, and for each envelope we assigned a random variable x, that took on a value 1 if a sale was made or we had a success, and a value 0 otherwise, we would say that this set of random variables x1 through xk is called exchangeable if the probability of x1 through xk is the same no matter how we permute them. So essentially, we can't tell before looking at the outcomes what the differences are. Exchangeability drives ideas like identically independent distributions and sufficient statistics. If our k variables were truly exchangeable, then the following is a sufficient statistic. Just knowing the count of how many successes we had is all there is in that information. We don't need to look for streaks or alternations because by exchangeability, we've assumed all permutations of the outcomes are equally likely. A summary statistic is not quite as strong as a sufficient statistic, but often once we make an assumption that we have a distribution at hand, one or more summaries completely determine everything we don't know. For example, if we assume our data is normally distributed, then knowing the mean and the variance completely determines the distribution. The mean, or also the expected value, is written E bracket x and equals the sum of all possibilities, the value of that possibility times the probability of that possibility happening. For example, if our 3 observations were 0, 0, 1, the mean or expected value is 1/3. The variance is the degree of dispersion or uncertainty of values about the mean. It is defined formally as the expected value of values minus the mean squared. For example, the variance of 0, 0, 1 is easy to calculate. The mean is 1/3, and the variance is then the longer formula beyond that, which is 0.222 or 2/9. The standard deviation is the square root of the variance, is 0.47, and it's very convenient because it's in the same units as the original thing to be measured. So if x were in dollars, the standard deviation is also in dollars. The rules of thumb that come with standard deviation, which largely come from lessons of the normal distribution, but are also true for many other distributions, such as the binomial and beta, is that being within plus or minus 2 standard deviations is quite typical, but being within further than plus or minus 5 is quite rare. Now, some things like the log normal distribution can violate some of these rules. As we've said, if you assume the form of the distribution, knowing a couple of summary statistics often tells you everything else you need to know about the distribution. We will actually only use 2 distributions to calculate. We will use the binomial distribution, which relates known rates and experiment sizes to possible outcomes, how many success counts we get. We will also use the beta distribution that maps known experimental outcomes to distributions of the unknown intensity parameter we're trying to measure. We'll also use the Poisson distribution to argue about how counts work and to build simple rules of thumb that we need to wait for 5 to 10 successes before stopping an experiment. Distributions we are not going to use are the normal distribution, which, as we said, is normally the basis of most statistical tests, and the log normal distribution, which is actually a harder to use distribution because values near its mean are not typical, as is one of the great properties of all the other distributions we were using. The idea is frequentist inference treats experiments as repeatable events that may generate different data. Most frequentist statements are about what would happen if we ran the same procedure again and again many times. Bayesian inference is a little less common, but quite standard. In Bayesian inference, the measured data is assumed to be held constant, and the quantity to be inferred is assumed to have some distributional property. As we get more data, we can tighten the distribution on the unknown quantity to be inferred. How will we use these statistical ideas to solve the response-based campaign problem? What we're going to do is we're going to consider a sales campaign as an experiment. We will assume, with some justification, we know what form the distribution of the outcomes have given the intensity and what distribution the intensity has given the outcomes. We use standard methods to estimate the parameters of these distributions. Once we have fit these distributions, we can then use them to answer additional business questions. The technique is called Bayesian estimation of posterior distributions. We will actually work through how that works and explain it after we demonstrate the technique using the worksheet. What we want you to take away from this lecture is sales campaigns can be thought of as experiments where we're trying to measure unknown rates of populations from observed counts and ratios in experimental data. Distributions are summaries of all possible outcomes of measurements. Summary statistics are quantities we can estimate from our data and then use as approximations for the unknown parameters of our modeling distributions. So once we know them or estimate them, we can work like we know everything we need. In the next lesson, we're going to work examples through the ready-made worksheet. The examples will make more sense in terms of these terms, and these terms will make more sense in the presence of examples.